Alright class, here it is. This is 3.3, 3.4 homework that you asked to do in class. So let's go for it. So 3.3 is up. Problem number 49. So problem number 49 has to do with, we're on the unit circle, and it says that the rotation starts at 1, 0. And the reason why it says that is because it has to start in standard position. Since it starts in the standard position, then we're able to rotate around and our theta and our t values match. So in this case, we go all the way up to that point there along the unit circle, and the reason why I know it that it is in quadrant 1 is because the x is positive and the y is positive. That's what I know. And it says the t value, there it is. So there's your stretch of the t value. And so the book says I need to find cosecant of t, and so you can go directly to the definition, right? The definition of cosecant of t would be 1 over y, or you can say 1 over sine, because it's a reciprocal function, and that would be 1 over y. So it doesn't matter really if you go to 1 over sine t and then 1 over y, or just go directly to 1 over y. That's fine. So the y coordinate, remember the r value is 1, right? So we don't have to worry about that. We are on the unit circle, so we are not worrying about r whatsoever. Alright, punch that into your calculator and you should get an answer of 1.1884, and that's what the book says as well. And I would probably take it out 4 decimal places just because your coordinates are in 4 decimal places. Alright, the next thing on the list is secant t. Secant t is same thing here, 1 over cosine t, which is 1 over the x coordinate, plunging that in, or taking the reciprocal of 0.5403, you get an answer of 1.8508. Alright, and the last one here, cotangent t. You can think of it as 1 over tangent, but that's really the long way around. Normally if you're going to do this on a calculator and you're actually trying to find the inverse tangent, you would do that. In this case, cotangent t, you just simply write as x over y. And so the x comes in, the y comes in, punch this in into your calculator, stop the video if you have to in order to do so, and voila, you get an answer of 0.6421, and that is what the back of the book says as well. Alright, jumping to 3.4, number 17. 17, it says these little sheaves. So the cable cars, the trolley cars in San Francisco, this is how they run. And so the cable itself comes in this way, and it starts touching the rotator right over here, the gears you can call it, comes this way, and then right at this point it stops touching the first one and starts touching the second one to go another 270, and then right here it leaves it and then it goes on to the next. So we know diameter is 14 feet, and it says, basically what we're trying to find is, it says how much of the cable is touching one of the sheaves. So we just take one of them, we know it's 270. So really this is an arc length problem. Alright, so let's go for it here. So 270 degrees, let's change that first into radians. And so I can knock off the degree signs, I can knock off the zeros, so 27 pi over 18. And then I can divide by 9, both of them. Looks like 9 is going to go into both of those. Voila, 3 pi over 2 is what I have. That's my theta measurement in radians. Okay. So arc length formula, real quick here, look it up if you need to here. It's S is equal to R times theta, and the radius, since the diameter is 14, the radius has to be 7. Theta, we just got is 3 pi over 2, and voila. Sorry, I should put in units here. How about 7 feet? And so, as I multiply this out, I should get an answer of about 32.987 feet, and I think the back of the book just lists it at 33 feet. So that's good there. All right. Jumping to the next problem here, this is 3.4, number 49. And it talks about finding the radius given the fact that you have an angle measurement of 30 degrees and you have an area that's inside there is pi over 3. Alright, so this is going to be the area of a sector problem. Area of a sector problem. So the units here are centimeters squared. And we are trying to find the radius this time, so we're kind of working our way backwards a little bit here. Alright, so quick formula here. A is equal to 1/2 r squared theta. Remember, theta has to be in radians. So we got one little problem there. And the other thing is, do you want to plug in the values now and then kind of solve it, or do you want to work with the formula and be able to put that together? That's the question. And just like chemistry class, we're going to do this here. We're going to set up the formula so we solve it for r, or at least r squared. That's what we want to solve it. So let's multiply both sides by 2. That means those guys on the right hand side are gone. So I got 2a is equal to r squared theta. In order to solve at least for r squared, let's divide by theta. So 2a over theta is going to give me r squared. Again, pause the video if you need to. And so now I got to take that degree measurement, since I'm ready to plug stuff in. I'm going to change it into radian measurement. Hopefully you guys can do this. Hopefully you have memorized this. So 30 degrees is going to be pi over 6. So let's go for it. I'm running out of space, but I still want to do it on the same slide here. So r squared is equal to 2a theta, or over theta. Plugging in the values here, I got a 2. I got a pi over 3 for the area. And I got a pi over 6 for the theta value. Sorry. 2. Pi over 3 is for the area value. Pi over 6 is for the theta value. So what I can do, I could make that into 2 pi over 3 divided by pi over 6, just making it as 2 fractions on top of each other, or complex fractions. And then I can change this to multiplication. So how about keep the first fraction, and then we take the reciprocal of the second fraction to change it to multiplication. And I think I see some stuff here. Pi's are gone. And also, okay, the 3 and the 6 can be reduced, or you can multiply it as 12 over 3, which reduces to 4. And remember, this is r squared, right? So that means if we take the square root of 4, it gives us 2. So I have 2 centimeters, and voila. There it is. I've solved it. Radius is 2 centimeters, given the area of the sector and the angle measurement. So we just kind of worked our way backwards on the formula. Alright, the next one, 3.4, number 55. It is talking about the bicycle wheel, the particular bicycle wheel that has spokes coming out. There are 22 spokes here, and the question really is, how much of the arc tends from one spoke to the other? That's the question. Alright, and so this is a arc length question, right? Because we're not dealing with the area inside the wheel, we're dealing with the outside here. So it says how much of the arc, how much of the tire tends from one spoke to another. Alright, so it also says that the diameter is 700 millimeters. So real quick here, that I know that the radius would be 350 millimeters. By the way, this is a common tire. In fact, I have a bike at home that's 700 millimeters. Common. It's more common in Europe, but we have those kind of tires too here on bikes. All right, let's go for it here. So I have the arc length is going to be the radius, which is given, and now the only little question for me is, how much of a theta do I have? Alright, here's a little trick. The trick is to say, you know what, theta is going to be, if I go all the way around, If I do 1 revolution, it's going to be 2 pi. But then I have 22 spokes on my hands, so it's going to be, for every single one, it's going to be 22 pi divided by 22. Because I'm dividing it into 22 pieces, because there's 22 spokes. And reducing it gets me pi over 11. Perfect. Now I can plug it in. That's theta, and theta in radians. And voila. So this is the exact answer, because I think the book asks for an exact answer. There it is. And it's in millimeters. And then also the book wants an approximate answer, so punch that into a calculator. This is what I got from my calculator. So then you just round it off and you get yourself 100 millimeters. Alright, next one, 3.4, number 65. 65, this is talking about the moon, right? This is the apparent diameter. Apparent diameter of the moon. This is kind of funny. You think of diameter as diameter, right? But what's really happening here, it says, as we mentioned in this section, for small central angles, circles with large radii, right? The chord and the arc are essentially the same length, right? Hopefully that's not drawn to scale. So the apparent diameter, the way we say it, is this little guy right here. It's a Greek letter. It's called alpha. You can also use the lowercase a. That would work too. Alright, so we want to know this guy. That's the apparent diameter. Alright, so let's work this out here. So it says, there's my chord coming down. Here's my arc sort of coming down. And they're fairly close, especially if you're looking thousands of miles away. So let's go for it here. So there's my alpha. And it says that the diameter of the moon is that number there, 3,470 kilometers. And then it says the distance from Earth to the moon is 384,000 kilometers. Alright, so how do we do this? Let me make a little diagram again here. Here's what I got. And notice this is arc length again, right? This is arc length. We are looking at this thing right here, and we're trying to find it's called apparent diameter, but pretty much the angle that is formed. Alright, punching it in. So I have S is given, alright? This is the arc that's on the face of the moon as we look at it here. Radius, that is exactly from the vantage point of the person looking to the moon itself. And we're trying to find theta. So as long as you see this, I think it'll be good here. Divide both sides by 384,000. And theta is given. Now remember, theta is in radian measurement. And it's very, very, very tiny. 0.009 radians. It says give the answer in radian form, also give the answer in degree form. So we're just going to take that number there. So in degrees, we're going to take that and we're just going to multiply it by 180 degrees, divide by pi, and punch that into a calculator, and you should get an answer of 0.518 degrees. Alright, and the last one, this was a question by one of the students here, is it was talking about the fact that if, let's say, if you have a lunar eclipse, right, the moon and the sun tend to look almost like the same size, and the answer in the back of the book just says they are 400 times further. So the sun is 400 times further than the moon. So explanation for it is this, like this. So let's say this is the sun that we're staring at. Oh yeah, sorry, it'll be a solar eclipse, not a lunar eclipse. So if we're looking from here, here's our vantage point right there. This is the sun, and the moon tends to do this right here. So as we look, the moon perfectly, almost perfectly, overshadows the sun right here. And it says, it's already given, it says that the sun is 400 times bigger, or at least the diameter is 400 times bigger than the moon. And the question is, well, how do you know it's 400 times of distance away? Alright, and this is because of, if you think back to your geometry days, this is just the same thing as proportional triangles or similar triangles. So let's say this, let's talk about the radius first. So we're just going to take this little piece right here, or this is the moon, let's say the radius of the moon right here. And this is the vantage point right here again. So remember, the diameter is just going to be double that, right? So if little d is the distance from Earth to the moon, and little r is the radius of the moon, what happens here? Ooh, do we have similar triangles? Absolutely. And so then this whole piece here is going to be big D, or the distance to the sun, and this piece is going to be capital R, or the radius of the sun. And so the reason why it's 400 times larger is because we have similar triangles on our hands. And with similar triangles, we have this little proportion. So the diameter, the small diameter divided by a large diameter, it has to be exactly the same as the distance. So distance, small distance divided by large distance, or the proportion between the two, has to equal the proportion between the radius of the moon divided by the radius of the sun. And so that's how we get the 400 times bigger. You can also write it a different way. You can write the proportion like this. It's kind of 4 different ways to write the proportion, but the distance to the moon divided by the radius of the moon is same as the distance to the sun divided by the radius of the sun. So you're going to get 400 that way as well. Alright, hopefully that was good. Hopefully that was helpful to you guys to finish up the homework.